If I want to calculate, for instance, the electric field produced by a bar, which is positively charged, and we're going to do it for positively charged, but it's the same for negatively charged, only the sense of the resulting electric field will be different. For the positively charged, the electric field at point P, which is located at the origin, will go towards this direction. For a negatively charged will be to the other direction. And we're calculating at a point P where it's located at a distance A from the extreme of the bar, which has length L. It is convenient to define that there is a density of charge, and we're going to call this lambda since it's a linear density of charge, and this is equal to the total amount of charge in the bar over the length, but it's also defined as a small piece of charge, which we call a differential of charge, over a differential of length. For instance, a small piece of this charge located anywhere of this bar has a differential of length. This is important because this is the definition of the density of charge. It is like the density of mass, but instead of relating mass over unit of length, we're relating charge. The generic distance from the origin towards the point we're analyzing, we're going to call it x, and we're going to be summing from a distance a to a distance a plus l. So if we define the electric field as the sum of these contributions, we're going to have an integral from a to a plus l of k dq over the generic distance, which is x squared. Now dl, which is the differential of length, is exactly the same as saying the differential of x, since we are working on x. The length and x is just notation, right? We must change the differential of charge, and in this sense we are going to state that lambda is going to be equal to dq over dl or dx, and then dx we can actually state it here such that in this case this will be equal to the integral from a to l, a plus l, k lambda dx over x squared. Now k is a constant, it can go out from the integral, and if lambda is a constant, it can go out from the integral as well. Otherwise, we can actually look for a function of the density with respect to x. In this case, then we have that the electric field is going to be equal to k lambda minus 1 over x, which is the integral of 1 over x squared dx, from a to a plus l, and if we evaluate the limits, we can actually get to k. Now lambda is charge over l times 1 over a minus 1 over a plus l. If we simplify this expression, we get that the electric field at any given point P, for instance, that is from one at a distance a from the extreme, is going to be k q, and this is going to be 1 over a plus l times l plus a, and this is going to be the electric field, the magnitude of the electric field. The direction, well, it depends if it's positive or negative, the charge.